Hi, my name is Gingfung. I'm a third-year PhD student at Lancaster University. Currently, I'm an intern at Alibaba. I'm grateful to get accepted into HotCloud, and today I'm going to present my research towards GPU utilization prediction for cloud deep learning. A typical deep learning system at companies or research groups have many machine learning engineers, researchers, and users. Each individual user may deploy many deep learning workloads, such as AutoML workloads, where each workload may have multiple models that are slightly different in terms of hyperparameters or model configurations. These workloads are normally ran on expensive GPUs due to the fact that they have thousands of parallel processing core and can perform teraflops per second, a floating point operation, which the deep learning models are mainly consist of. So in order to maximize cost efficiency, we must maintain a high efficient resource usage and high performance for these workloads. So what are the current challenges in this space? In a recent production study at Microsoft, where the average GPU utilization within the system is around 52%, this is implying that almost half of the GPUs are not used. Since we want to maximize cost efficiency, we want to improve this utilization value. The job completion and queuing times can go up to hours. This is undesirable if the system have many workloads queuing up. However, these challenges can be addressed by understanding and exploiting workload patterns. And how do we obtain these workload patterns? Online profiling approach may be conducted by deploying a workload into an isolated machines and GPUs. And then a resource monitor will continuously profile and monitor the response. And usually, per workload profiling range from minutes to hours depending on the metrics we want to obtain. For example, for kernel hardware counters may go up to hours. So what other metrics are important in deep learning system? Iteration time are particularly important for scaling out workers when we want to estimate how many workers we need. And we also can decide on when to migrate. We can also have SLA aware inference, so we can keep the inference request within a deadline. For network input or output, it is important for distributed training, where we want to minimize the communication between workers to avoid too many network hops. For GPU utilization, it is important when we want to maximize the cost efficiency, because if we identify that there's a GPU with low utilization, we can collocate multiple workloads together, and after we have packed them together, interference may be introduced. Therefore, we can look at the utilization value and the patterns to identify which process are being bullied. So, in a larger scenario, as mentioned before for migration, a scheduler would query the resource monitor, and after it has done its internal scoring and identify that there is a GPU with enough capacity, it would migrate the workload to the available GPU to empty out the space to make space available for larger workloads, so can keep the workload throughput faster. So as mentioned before, if the system has many heterogeneous workloads, this will lead to head-of-line blocking, because for individual workload, we would have to profile them for a couple of minutes. In the worst case, it will go up to hours. So in summary, online profiling have the following pros, which is they can provide insights to the system, and they are accurate. However, for heterogeneous workloads, it requires different profiles, and it may be time-consuming, ranging from minutes to hours, and in some cases it requires modifying underlying frameworks such as TensorFlow, PyTorch, or MXNet if we want to expose the iteration time. So we asked the following question: can we obtain a metric without execution, and can we do it for heterogeneous workloads? Our answer is we can utilize prediction, because for individual workload, if we can extract the features and feed into a predictor, then the inference of the predictor only takes around a couple of seconds. In the best case, is sub-second, and this can reduce a substantial amount of head-of-line blocking. So, going back to the challenges, because we want to maximize the cost efficiency, so we focus on average GPU utilization, and the following presentation will talk about how do we predict the GPU utilization. So the objective is we create a prediction engine for cloud deep learning systems. The benefits of it is it can estimate the utilization for unseen workloads prior execution and without modification of existing deep learning frameworks. And the following, we will present our objective in the following steps. Analysis. We first present our analysis, then we present the prediction model, and then we present the case study. So first, we identify that deep learning workload is typically a graph, specifically a directed acyclic graph, where there is one or many inputs to one or many outputs. The intermediate node within the graph can be identified as a deep neural network operation, such as convolution, linear matrix multiply, or activation functions, ReLU. Therefore, if we leverage the graph and traverse the graph, we can extract a lot of information. And you can see our paper for the full features list. So in order to determine the important model feature, we first created a custom benchmark with 13 deep neural network model architectures, and we permute them so that we can have 81 workloads. And our system setup have NVIDIA 1080 GPUs and NVIDIA 2080 GPUs. The tools we use are NVIDIA SMI to obtain the utilization, and NVIDIA Nsight system to look at the kernel access patterns. So as mentioned, our workloads have diverse range of flops and utilization, and we show that here because we want to capture whether there's underlying relationship between the two. And it is shown that when the flops increase, the utilization may also increase. This could be due to the fact that when a model is more complex, i.e. having more computation, more feature maps, it generally requires more floating point operations. And because it requires more computation, it means that the GPU need to do more work, hence a higher utilization. And we carried out a preliminary analysis where on the left is a collocation experiment where we put two models together on the same GPU to capture any interference relationship with their GPU utilization. And we show that there is a 1.5 times to 4 times increase as slowdown by just looking at the utilization alone. So it's a good indicator. On the right is an architecture analysis where we ran the same model and same data types on two different hardware architecture. And we show that there is indeed a difference. This may be due to the fact that the NVIDIA newer architecture have higher number of processing cores, cache sizes, and bandwidth. However, it is not always intuitive because ResNet 50 is have the same utilization on both 1080s and 2080s. This may be due to the CUDNN deep neural network libraries optimizations. And we also want to stress that for the collocation experiment, the slowdown may be due to the fact that the NVIDIA kernel scheduling is application round robin, first in, first out. So meaning that it has to wait for an application A to finish their kernel, then the application B start their kernel. So now that we determine utilization is important, so how do we predict utilization? So as mentioned before, we try first the deep learning computation graph. For each node within the graph, we take the input node and the output node, and we calculate the relevant features by extracting the inputs and the outputs and look at the parameters of that current node. Then we can calculate the features. In terms of floating point operation, we can look at the input shapes and output shapes, and then we can calculate the number of floating point operations we need. Finally, after we calculated all the features we needed, we can feed into our regressors, and we evaluated a number of regressors. We find that random forests perform the best. This may be due to the fact that our custom benchmark has more convolution neural network than recurrent neural network types. And in the future, we will investigate more diverse deep neural network architecture. We use the error function root mean square log error because we want to penalize underutilization. In a pessimistic approach, we do not want to have a prediction value that will tell us that we underestimate the utilization because the impact is causing higher slowdown of a particular workload. Next, we integrated our prediction engine into a resource manager, Kubernetes. We modified Kubernetes so that our scheduler can collocate multiple workloads onto the same GPU. We put our prediction engine into the cluster scheduler because we want to show that the approach that we propose can drive a higher average cluster GPU utilization. The workflow is as follows. When we submit a workload definition, we also submit the computation graph, and we extract the features, feed into the predictor, and then the predictor can predict the value and attach it back to the definition. When the scheduler looks at the definition, it will look at the utilization value and use a first fit decreasing algorithm to pack workload onto the same GPU. We also evaluated our approach against default slot-based Kubernetes scheduler where it disables collocation. And we also evaluated our approach against reactive online profiling where each individual workload has to be profiled for 1 minute to obtain a stable utilization pattern. And you can see that our approach achieved the highest average cluster GPU utilization with also the fastest mixback. This is desirable because we essentially address the two challenges mentioned before, the cluster utilization problem and long job completion and queuing times. So what are the open challenges in this space? Currently, our approach do not consider hardware features, for example, the number of processing elements, memory bandwidth of the device, and the cache sizes for the level. We also do not extract lower-level intermediate representation from the compilers. This may be desirable in the future because compilers now will optimize the graph. For example, fusing multiple operations together into one operation, such as convolution, batch norm, and also activation. Currently, we also do not consider distributed workload, and in the future, we might want to consider network I/O, parallelism strategy, and system configuration, and we want to investigate what can these factors affect the utilization metric. Finally, we want to investigate how we can incorporate our prediction and system constraint to derive a better collocation scheduling strategy, such as deriving an mixed integer programming approach. Finally, we conclude that existing resource-efficient decision in deep learning system require online profiling on isolated machines. This is undesirable, and we propose an approach to predict the utilization value for deep learning workloads before execution. And our approach achieves an overall average 69% GPU utilization in comparison to 43.1% slot-based and 47.1% online profiling reactive approach. Thank you very much, and we hope to receive questions from you guys. Thanks.